Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Aneel Prasad Sir, and in this session, I'm gonna give you people a perspective towards this entire computer architecture and organization. So far, I've covered you a few topics, but before which, you people might have no idea. Rather, you people have got some idea towards this computer architecture and organization. Am I audible? First of all, I don't know if I'm audible or not. I don't know. I think there's something not going correct. Let me correct the stream, and I guess there is some problem with the stream. Yeah, of course. I guess my voice is low. Hi, BD Villas. Hi, Anu CS. Now, if this is audible, if you let me know if this is audible, I will continue. Somebody please let me know if this is audible. Krishna or ABD Villas or Veena or Anu, I want you people to let me know if I am audible or not. Yeah, fine. So let us start. Once again, welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Aneel Prasad Sir, and in this session, I'm going to give you a perspective towards this computer architecture and organization. First of all, let me tell you something. That is, so far, I've covered quite a few topics in computer architecture, and in which you understood, the people who following my classes regularly, they got some perspective towards it. Right from this session, I'm going to give you people a complete perspective towards this computer architecture and organization. For that, the prerequisites are the same. I don't expect you people to learn everything. Hi Tushar, hi Krishna, hi Abdullos, hi Anu, and hi Veena. Yeah, sorry for the inconvenience, sorry for the technical glitch. I was unaware what exactly is happening here. Now it's going good. Now let us understand something. Here in this topic, let us start with the basics of the computer architecture, because right from here you may be preparing either for your university exam or for the GATE exam. It doesn't matter. Right from now, right from exactly at this point, at today, standing here, I'm gonna take you people into the world of computer architecture and organization very easily indeed. So it will be helpful in twofold. The first one is for your GATE exam straight away. The second one is we'll also be able to give you university exams, and you will be able to score really good. Only the thing is, if you are able to focus on the class quite good, that's it. With earphone. So sorry, your laptop use karo. Good evening. Yeah, fine. Now, voice is low. Voice is low. I don't think the voice is low. I don't think the voice is low. I guess the voice is quite good, I guess. Now, let us start. So this is, it's about myself, the people who follow my classes. You know about my expertise, and I don't want to waste the time here, because due to the technical glitch, quite a bit time that's been wasted. Now, let me take you people into the session directly. Now, Just a minute. Now then, listen something. Here, first of all, let us understand the computer architecture and organization is all about designing the CPU, alright? Designing the total computer system. Again, if you ask me, sir, what is there to design? You need to understand, first of all, the design of the CPU. Next thing is, we need to design the main memory, followed by, we need to talk about the design of the peripheral devices through which we'll be able to communicate with the computer system. Now, in this session, I'm going to cover quite a bit of basics. Here, within the CPU, again, there are several things that is needed to be designed. First of all, we need to design the register set. Hi, I'm Nishu, old student of BYJU'S Exam Prep. Hi, hello Nishu. Once again, yeah, listen to me very carefully. Let us dive into the session. But before that, please like, share and subscribe to this channel without wasting any more time, because right from now, right from this point, you're going to get many classes from the BYJU'S Exam Prep, especially for computer science people. We are coming up with more and more exciting sessions. So, and if you haven't yet already, please subscribe to this channel and share the session as much as possible. So, let the other people also exploit this session. Now, so once again, before I take you people to the CPU architecture, first of all, what is needed to be designed? The thing that is needed to be designed in the CPU is only three. The first one is the register set. Second one is control unit. And the third one is the ALU. What is the register set? A register set is used for the intermediate storage purpose. Every instruction, when it is being executed, in order to execute that instruction, we are going to bring the data that is related to the instruction into the CPU. Next thing is, we need to design the control unit. What is control unit? The control unit talks about the flow of the information. During the every instruction execution, there has to be the data flow. There has to be some data should be transferred from one location to another location. Finally, an instruction must get executed. Let me tell you something. All of you people, are you with me? Let us understand something very carefully. If you ask me, sir, what is the job of the computer system? Our computer system is going to serve for only one job, that is instruction execution. You can't talk about a program execution. You can't talk about a software, or you can't talk about anything else rather than executing one instruction at a time. When you talk about a CPU, that is the job of the CPU all the time. Now, I'm a CPU. What is my job? If you press a pause button, if you open your cabinet and if you have a look at the CPU's simple job is it executes one and only one instruction at every instance. Alright? So, right at the end of the one instruction, when the instruction gets executed, it is going to get the next instruction, followed by the next instruction, followed by the next instruction. It is the redundant job of the CPU all the time, repetitive job of the CPU all the time. So, you can't talk about anything else. When you want to understand the computer architecture, no matter for how many number of times I tell you, if you actually can understand the instruction cycle, you are done. You are going to make the total computer architecture design very simple indeed. I've been telling you, if you are my old student, you've been, hello Chitra, nice to see you guys again. Yeah, if you are my old students, you know that I've been telling you guys from many times. So let me tell you. So here, I mean, control unit design. Control unit exactly talks about how the data is going to transfer from one location to another location. What we are talking about? We are talking about the instruction execution, right? During the instruction execution, data will have to be transferred from one location to another location. Initially, where is the instruction? The instruction is in the main memory. Instruction is initially at the main memory, right? Instruction is not directly available within the CPU. Instruction is actually at the main memory. From the main memory, we are going to bring that instruction into the CPU. This job will be done by the control unit. The control unit will initiate these transfers. The moment it comes into the CPU, the instruction requires some other data. So that data will also be brought into the main memory, from main memory to the CPU registers. Right after which, finally, the control unit should instruct the ALU what job that is needed to be performed. This is the actual job of the control unit. And then, obviously, we know about the ALU design. We know what is the ALU is really capable of. And finally, excuse me, the ALU is going to perform arithmetic operations. In arithmetic operation, there will be addition, subtraction, and finally we are also going to have a logical unit. So this is not our job right now. Now initially we are going to talk about the different types of the. Let us have a look at. For that, in order to understand all those things, first of all, I request you people to focus on the screen straight away. Yeah, stay focused here. You can see the instruction memory, right? This is the instruction memory. This is the data memory. When you talk about the memory, initially the total memory will get divided into two parts. One is instruction memory and one more is data memory. What is instruction memory? Instruction memory, instruction memory is going to hold all the instructions. Whatever the program that is being executed, all those programs will get loaded into the instruction memory, and this is contiguous. What is data memory? The data memory is going to hold all the data elements initially. Every time when you want to execute an instruction, that instruction must have some operands for execution, right? So the data part, the operands part of any program will get stored into the data memory, and the instructions of any program will get stored into the instruction memory. The instruction memory is contiguous. All the instructions of any program will be aligned one after another. That means that if one instruction is being executed right now, that is at the 23rd address of the main memory, the next instruction will exactly be aligned at the 24th location. But the data operands that belong to these instructions will be available within the data memory. Those are non-contiguous. Non-contiguity meaning 23rd instructions data operand may be available in some address, 24th instructions data operand may be available in some different address, may not be right at the contiguous location of the previous operand. So this is all about the non-contiguity. This is how the instruction memory and the data memory get stored in the main memory. Now, rather instruction memory and data memory are going to hold the instructions and data elements. Excuse me, why my pen is not writing? Let me. Yeah. Yeah. This is instruction memory, will hold the instructions part. This is the data memory, will hold the data part. Operands will be non-contiguous. Instructions will be contiguous. Now let me tell you. In order to understand any architecture, any CPU, first of all we need to take a counter example of a CPU. Now, total computer architecture I am going to explain you from the perspective of a simple CPU. In the simple CPU that we are designing, the architecture size is equal to 16 bits. The CPU, the example size of the CPU that I am taking is a 16 bits. 16 bits meaning simple. Sir, what is architecture size? Architecture size meaning one word in the main memory. One word in the main memory is equal to 16 bits. That means a register size within the processor is also equal to 16 bits. This is what all about the architecture size. No matter either it's a memory location or a processor's register. If you want to exactly understand what is your architecture size, go and have a look at one word length. Word length will be either 8 bits or 16 bits or 32 bits or 64 bits. It could be, it is different from architecture to architecture. When you go back to the Intel processors, all the Intel processors of 32 bits. Nowadays we are seeing also 64-bit processors. And before that, when you talk about 8086 or 8085, most of the previous days architectures supported 16 bits. That meaning 2 bytes within the main memory are organized as a one word. But here, while we are discussing, I am going to take an example of a CPU which is of 16-bit size. That meaning one word size is equal to 16 bits. Okay. So memory, of course, as you know, memory size will be different from system to system. Obviously, I mean, now in your system, the main memory may be 2 GB. In my system, main memory is of 4 GB. In somebody else's system, main memory is of 8 GB. For that, I mean, in order to completely understand the computer architecture, we also need to take an example size of the main memory. The example size of the main memory that I am taking is 4096 words. That means that memory will be addressed with the 12 bits. Any doubts so far? Sir, what is this 12-bit address? Let me tell you. See, this is my total main memory, right? Let me erase this. This is my total main memory. Okay? Total size is equal to 4096. Meaning this is the 0th location, this is 4095th location. Got me? That means that I do require an address length here. I need some address digits that are actually needed to represent every location. For that, I require 12 digits. What is 12 digits? Total 4096 is equal to 2 power 12. How to represent an address? An address will be represented by using the binary digits. So, if you take 12 digits for a 4096 memory, you will be able to address every location starting from 12 zeros to 12 ones. I hope you got it already clear. Any doubts, you can ask me right now. Now, addressing conventions, every byte can be given an address or every word can be given an address. It is not right now. I'm gonna explain you because I already explained you about byte addressing or word addressing in the previous classes. So please access my previous sessions in order to understand word addressing and byte addressing. Now, let us understand something. See, one fundamental rule to execute any program within a computer system is, first of all, you should be able to bring that program into the main memory. I want you people to participate. Initially, we had some glitch and which took some time. But whenever I take a session, I want that session to be more and more productive. When that is going to happen? Whenever you start participating. Whenever you have a doubt without having any time wasted whatsoever, I want you people to shoot the doubts initially within the chat box itself. Right after which, if you get any doubt, I ask you people to post your doubts in the comment section. At the end of every session, I'm gonna leave you people with some kind of other work. For that, I want you people to do the homework what I gave you, and I just want you people to post the answers in the comment section. So let this session, all the upcoming sessions be more and more productive. So understand carefully. What is stored program organization? Fundamental rule of a computer system will tell you, will tell the Tushar, A.B. de Villiers, or Chanchal, or Chitra, or Anu, bring your program into the main memory. If you can't bring your program into the main memory, there is no ever for you to execute your program. If you have a program, please bring it and keep it into the main memory. That is the only way that you can execute your program. Now, see, here the thing is, when you talk about stored program organization, all the instructions will be stored in the main memory. Of course, every program will need to get stored into the main memory. A program is equal to a set of instructions, right? Each and every instruction will be stored into the instruction part of the main memory, aligned one after another. Right after the first instruction, there has to be second instruction. Right after the second instruction, there has to be third instruction in a sequence. Okay. Now, let us understand something. What is the size of the instruction? Size of the instruction is, excuse me. Yeah. What is the size of the instruction? Size of the instruction is 16 bits. Why 16 bits? One memory location is equal to 16 bits. So now have a look at this instruction. See, what you're watching here is an instruction within the main memory. Okay. One total instruction is of 16 digits, starting from the 0th digit to the 15th digit, in which there are 4 digits that are given for the opcode. 0 to 11 are given for the address. Now, the architecture that we are considering is a single accumulator organization architecture. What is single accumulator? In the single accumulator organization, we do have the instructions with only one operand. Every instruction will have only one operand. Any doubts so far? That means that every instruction will have one opcode plus one operand. That's all. Sir, where is the second operand? Let us say there is addition. I want to perform addition. In order to perform addition, I require at least two operands, right? One operand is provided within the instruction in some or the other form. Second operand will not be provided within the instruction. Rather, it is always a processor's register which is accumulative. I explained you about this phenomena already in my previous classes, but fine. Let me explain you for one more time. Here, I am taking the counter example of a single accumulator organization system. In the single accumulator organization, I do have a 16-bit instructions. All the instructions are of 16 bits, in which first 4 digits are the opcode and next 12 digits will give you a memory address of the operand. Okay, so one operand will be provided with an instruction in the form mostly in the form of an address, memory address. The second operand is always accumulative. I hope you got the point. So let me not hang around this. Yeah. Now, there are several registers here. In the single accumulator organization, I do have altogether a total of 8 registers: program counter, address register, instruction register, temporary register, data register, input register, output register, and accumulator. Again, let me brief you about the purpose of each and every register here very clearly. Program counter will hold the address part of the next instruction. If the current instruction in the memory is 22, currently CPU is executing 22nd instruction, program counter will hold the address of the next instruction, that is 23. Address register will hold the memory addresses whenever a CPU requires to access the data from the main memory. CPU always talks to the memory by using an address. That address that is needed to be sent to the main memory initially will be given to the address register, since address register can directly communicate with the main memory. So this is all about the address register. Any doubts whatsoever? Any doubts so far? Okay, next thing is the instruction register. What is the job of the instruction register? The instruction register is going to store the current instruction that is being executed. Now, let us say CPU program counter is holding 23. That means that CPU is now executing 22nd instruction. The instruction is held by the instruction register. Current instruction that is being executed by the CPU all the time will get stored into the instruction register. So, data register is going to hold one operand, accumulator is going to hold one operand, and one operand is always accumulator. Second operand will be brought to the data register. So these are the basics that I want to explain you people for one more time, taking the help of my previous classes. In my previous classes, I explained you people each and everything. Right now, having explained all these things, I want you people to understand the design of the opcode. This is the very purpose that I am taking this class right now. My purpose of taking this class right now is not to explain you people about registers, since I explained about the register already in my previous class, one of the previous class, and I explained you about what is the purpose of all the registers, how the instruction is going to be executed, what is the instruction cycle. Now, let us start designing, yes, let us start designing the opcodes directly. What are the opcodes? In what way the opcodes are actually designed for a processor? Let me tell you something very carefully, and you just listen to what I am explaining for the next 5 minutes very, very carefully indeed. Listen to this. You do have, here is the address register. You do have a program, right? Always you're going to execute your high level language programs. When a high level language program is getting executed, this high level language program must get translated to a low level language, a machine language program. What is a machine language program? Let me tell you. In your C program, you're executing one instruction called printf, or you're executing one instruction called add a comma b, or you're executing some more instruction, or you're executing some more instruction. Let us understand something here. Let us understand something here. Each and every instruction of your high-level language needs to be translated to its corresponding and equivalent machine language instructions. For an instance, there is an addition instruction. In C, you are executing addition instruction, add instruction. But this add instruction cannot be executed directly by the CPU. In order to execute any instruction, it must get converted into one or more machine language instructions. I would say opcodes. Okay. So, in order to execute one high-level language instruction, either it is addition or a printf, it needs to get translated into corresponding low-level or machine language instruction, can also be called as the opcodes. Okay. For that purpose, every CPU, no matter whatever you take, either you take Snapdragon or you take Intel Atom or you take i3, i9, 8086 or 8085, each and every processor must be provided with a few machine language instruction. We are going to design in this session those machine language instructions. Got me? Yeah. Let us understand what you're watching on the screen is a bus system. Before I take you people into the actual design of the machine language instructions, let me show you the bus system here. Is it visible here? First of all, I do have a memory unit. Okay. I do have an address register. I do have a program counter, data register, accumulator, input register. This is instruction register, temporary register, output register. Now let us understand. These are all interconnected by using the bus system. Is it visible? Is it visible? Is the bus system visible on the screen? Is the bus system visible on the screen? Is it visible on the screen? Okay, fine. See, this bus system is going to select these registers. Whenever these registers are selected, the contents of these registers will be transferred from one location to another location. For instance, I want to transfer the content from the memory location to address register, or from address register to the program counter, or from the program counter to the data register, or from data register to the accumulator. I want to make a transfer. For that, I require to use a bus system. You can see bus system is designed with some multiplexers. There are selection inputs. 3 selection inputs, S0, S1, S2. If these are equal to 000, one register will get selected. For instance, what is the first register? The first register is the address register. If it is 000, address register will get selected. If it is 001, program counter will get selected. I hope you got the point. So, likewise, the bus system is going to select these registers and is going to make the transfers accordingly. And one more thing that you need to understand at this point is, every register is going to have 3 inputs. What are those? Let me show you. One input is, there are 3 inputs you can see. One, this is a memory unit. I am talking about, let us take address register. There is one input, second input and a third input. First input, second input, third input. Inputs are, let me tell you, INC, load and clear. If INC gets enabled, the contents of the register will get incremented. Load gets enabled, the contents will get transferred to the specific register. The register which is enabled with the load input is going to get the data from the bus system. Clear meaning, whenever clear input gets enabled, the current register contents will be cleared. I hope you got the point. Okay. Now, yeah, let us understand something. Here, I want to explain about the memory reference instruction. Now, let us dive into the topic of designing the opcodes. As I told you, we need to design the opcodes, right, for every processor. Let me tell you something. while you are executing any instruction, we require some operands. Any instruction, take any instruction. Chanchal is control IP. Yes, I am not getting what you're talking about. Please be precise if you do have a doubt. Just listen to me right now. For the next, as I told you, I want you people to keep your pen aside and just listen to me. So far, we just revised whatever happened in the previous classes. I revised, right? We just had a recap, a quick recap. But now I'm gonna take you people into design of the opcodes directly. Okay, understand something. When you are executing an instruction, you require an operand to be fetched. If you want to perform addition, you require an operand, right? One operand is always accumulator. Second operand in a single accumulator organization, one operand is always accumulator. Second operand will be there within an instruction. Okay. Now, when you want to perform an arithmetic operation, we require operands. First of all, understand, we are not performing operation on a pen and paper by using a pen and paper. These operands will have some specific locations within the computer system. Let me tell you, the total opcodes can be actually classified into 3 different categories. The total opcodes, no matter how many opcodes you design and define, all these opcodes based on from where they are fetching their operands are divided into 3 classifications, 3 categories. The first one is memory reference instructions. Second one is register reference instructions. And the third one is IO instructions. Sir, what is this memory reference? What is this register reference? What is this IO instructions? Please explain. I will if you stay focused very clearly. What is the memory reference instruction? For any instruction, if the operand is available within the main memory, then that means that that instruction is a memory reference instruction. I hope you got the point. Accumulator is used for arithmetic operations. Nope, Anu, where are you? Don't sleep. Accumulator is not used for arithmetic operations. For arithmetic operation, we use ALU directly, but some basic arithmetic operations can be performed within the accumulator itself. Accumulator holds one operand. I agree with you, Anu. Let me correct you. Accumulator can be called as an arithmetic register, but it is not used for all the arithmetic operations. If you want to perform the arithmetic operation, we do have a guy. He's the ALU. His job is to perform the operations, but basic arithmetic operations can be performed by the accumulator. I hope I made it myself clear. Did I or not? Okay, so stay focused. There are 3 classifications, right? Memory reference, register reference, and the IO instructions. Okay, understand carefully. Memory reference meaning, for those instructions, operations are available within the main memory. Register reference meaning, for those instructions, operands are available within the processor's registers itself. IO instructions meaning, not only for executing the instructions, we use the IO instructions for several purposes. For establishing a communication in between the CPU and the peripheral devices, for making a transfers from the CPU to the peripheral devices, for receiving the data from the peripheral devices, or transferring the data to the peripheral devices, or enabling the interrupts or disabling the interrupts. IO instructions is a separate category. We will talk about the IO instruction later, maybe tomorrow or day after. Okay. Now let us understand something. Hi Kamlesh. Very good evening. Now understand about the memory reference instruction. Within no time I'll explain you what is a memory reference instruction. Stay focused. Understand that's how many bits we do have in the opcode. Once again, let me tell you total number of bits. Yeah, here I will take one location of the memory is equal to 16 bits, right? In the 16 bits, let me divide this total 16 bits into 3 fields. First bit, next 3 bits, least significant 12 digits. These are the least significant 12 digits. These are the next 3 digits followed by 1 digit, the first most significant digit. Let me tell you, least significant 12 digits most of the times is going to hold an address. Next to least significant, most significant 3 digits, right after these 12 digits, these 3 digits are going to hold the opcode. This 1 digit is used for mode. Okay, if it is 0, it's a direct addressing mode, or if it is 1, it is an indirect addressing mode. Now, altogether, we do have a total of 3 bits for the opcode, right? We are left with 3 bits for the opcode. That means that we can have a possible of 2 power 3 opcodes, which is equal to 8, right? So that means that for my system, I can construct the total number of opcodes altogether equal to 8, 000, 001, so on, 111, right? Each combination can be assigned to 1 opcode. Did I make it myself clear? Each combination can be assigned to one of the opcode. I hope I made it myself clear. ABD Villiers, are you here? Nishant, what's your name? I forgot. Nishu, I guess, right? So, total number of bits for the opcode is equal to 3. That means that we are left with, rather, we will be able to construct a maximum of 8 opcodes, 000 being the first one, 111 being the last one. Got me? It's not 4 bits, it's just 3 digits. First digit I have given for the mode digit. Okay. If mode digit is 0, then that is the indirect addressing mode. If the mode digit is 1, that means that, if mode digit is 0, that is the direct addressing mode. If mode digit is equal to 1, that means that it is an indirect addressing mode. You got me? Yes. Good. Very good. Now, let me tell you about the memory. Let me talk about now about the memory reference instructions. Stay focused now. Okay. Eraser. Let me erase all these things. Stay focused all of you. Here the thing is, see, let us only talk about the first 4 digits. First digit is a mode digit. I don't need to talk more about this mode digit. 0 indirect addressing mode, 0 direct addressing mode, 1 indirect addressing mode, right? Okay. Now, I divide my total opcodes into 3 categories: memory reference, register reference, and the IO instructions. What is memory reference? For all the memory reference instructions, operands are available within the main memory. For all the register reference instructions, operands are available in the processor's registers. IO instructions, operands are at IO devices, but IO instructions are not just to perform the operations. IO instructions are also used for some transfers. Now, let us talk about the memory reference instructions. Now, let me tell you, the combinations, the total combinations are 8, right? Okay. Here in the among all the 8 combinations, I am using 1, 2, 3, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 101, 110. Total number of memory reference instructions are 1, 2, 3, 4, 5, 6, 7. Here, I am not using a combination of opcode 111 here. That means that if the opcode is 111, it is not a memory reference instruction. It is either a register reference or an IO instruction. So, we are not including 111 opcode here. The opcode which has a combination of 111 here, since 111 is not falling under memory reference instruction. In the system that we are designing, we designed a total of 7 memory reference instructions starting from 000 to 110. If it is 111, if you had a look at the opcode which is equal to 111, you can directly say me, you can directly tell me, sir, this is not a memory reference instruction. When you execute the instruction, operand is not available in the main memory. I hope you got the thing. Okay. Now, see this. Listen. If the opcode is 000, that means that the operation that is going to be performed within the system is AND operation. If the opcode is 001, the operation that is performed, that is going to get performed is addition. If 010, the operation that is going to get performed within the system is load. 000, 001, 010 is load, 011 is store, and 100 is BUN. What is BUN? Branch unconditionally. BSA is branch and save the return address. ISZ stands for increment and skip F0. Okay, that is 110. Okay, so what is this AND operation? AND operation is an AND operation. Already you know what is an AND operation. What exactly is the AND? AND operation is going to perform an AND operation in between two operands. One operand will be within the main memory. One more operand is accumulator itself. For instance, there is one operation which is called AND 360. That means that finally the operation that is going to be performed is accumulator is equal to accumulator and memory of 360. Okay, so we will get the operand going to the memory location 360. Right after we get the operand, it will be ANDed to the contents of the accumulator, and finally it will get transferred to the accumulator. So here the thing is the implicit operand and the destination operand for all the instructions will always be accumulator. Similarly, addition. So when opcode is equal to 001, addition will get performed. When the opcode is 010, load will get performed. What is load? Could you please tell me what is load? Some of my regular students, you will be able to tell me what is the load instruction, or you want me to explain? What is the difference between load and store? Yeah, let us understand. Load 360, meaning from the memory location 360, the content will get transferred to the processor's register, in our case accumulator. Store 360 meaning it acts exactly opposite to load 360. The contents of the memory location in the load case will get transferred to the accumulator. Store meaning the contents of the accumulator will get transferred to the contents of the accumulator will get transferred to the main memory. So that is when you say store 360 from accumulator to memory of 360, contents will get transferred. I hope I made it myself clear. Okay, is my voice audible? I don't think it is buffering. It is good now. Okay, that is the difference between load and store. Now, what is BUN? BUN stands for branch unconditionally. I think you have some jump instructions in your C programming, right? When you execute a high-level language program, you will have some jump instructions. The jump instruction will have to skip during the execution of the jump instructions, the control will be transferred from one location to another location. Simple. During the jump instruction, the program control will be jumping to some other location. For instance, let us say I want to perform BUN 300. let us say current instruction. This is an instruction within the main memory, okay? This is the current instruction 23. Right after this instruction, which instruction we need to execute? 24th instruction we need to execute. This instruction is available at the 23rd location of the main memory. Now, right after we execute this 23rd instruction, we generally need to execute 24. But this BUN is a corresponding and equivalent instruction to the jump instruction of the high-level language. So, when jump instruction gets executed, the corresponding instruction, that is BUN within the low-level processor, will get executed, at which the control will take you to 300 location by skipping all the intermediate instruction. Directly, you are going to execute 300 instruction by skipping all the intermediate instruction. BUN stands for branch unconditionally. I hope you got the point. Yep. Similarly, there is one more instruction called BSA. Now, right after BUN, we also do have one instruction called BSA. Let us say this is my main memory. In the main memory, current instruction is 23 and current instruction is BSA. BSA 300. The difference between BUN 300 and BSA 300 is BUN is an equivalent instruction to jump. BSA is an equivalent instruction to call instruction. What is call? Here we are calling a subroutine. Jump is unconditional, but this is conditional. Whenever we perform a call instruction, automatically there will be an embedded condition. What is an embedded condition? Embedded condition meaning right after you perform the call instruction, you will be taken to a subroutine. Right after you execute the subroutine, you need to return back to the calling routine, right? This is the routine from where you are calling a subroutine. Subroutine is available from the 300th location. So you will go to 300. From 300, there is a subroutine originated. So this is the origin of the subroutine, during which your subroutine will get executed. Let us say subroutine is from 300 to 400. Right after you execute the final instruction of the subroutine, you are expected to go back to the calling routine. This is the calling routine, this is the call routine. Right after the call routine has been executed, we need to go back to the calling routine from where we suspended the next instruction, that is 24. Okay, so 23. If 23rd instruction has a jump instruction, simply you will jump to 300 and you go ahead from that. But if it is a call instruction, which is a BSA instruction, you will go to 300 anyhow, by all means. But right after you finish your subroutine, you will return back to the calling routine from where the routine has been suspended. We just executed 23, after which we went to subroutine by suspending the next instruction, which is 24, right? So we need to resume from the 24th instruction. So this is the difference between jump and call. Call is BSA, jump is BUN. Any doubt so far? Excuse me. Yeah. Next thing is ISZ. What is ISZ? ISZ stands for increment and skip if 0. I'll explain what exactly is this ISZ. For that, I need to erase. Understand what exactly is this ISZ. Let us say this is an instruction. Okay, this instruction is at 23rd location. Current instruction is 23 and the program counter value is equal to 24. The current instruction is increment and skip if 0. ISZ 360. Okay, so during the ISZ instruction, what we will do is we will go to 360th location of the main memory. In 360th location, we do have some content over there. There is a data element, there is a data operand. The data operand, let us say it is 40. What we need to do is we need to increment the memory value of 360. Right after incrementing, if the value equals to 0, we need to skip the next instruction. That means ISZ stands for increment the operand. What is the operand? Operand is available within the instruction in the form of an address. We need to go to that address, collect that operand and increment the operand. Now operand is equal to 40. Incrementing the operand meaning 40 plus 1 is equal to 41. Right after you increment the operand, if it is equal to 0, then that means that we need to skip the next instruction. But here in this case, next instruction need not be skipped at all, since when you right after you incrementing, the operand doesn't become 0. If the operand becomes 0, you don't need to execute the next instruction. Rather, you will start with the 25th instruction. This is what ISZ all about. What is ISZ? Increment the operand. Right after you increment the operand, if the value becomes 0, please don't execute the next instruction. Otherwise, you please execute the next instruction. Here in this case, as the operand doesn't become 0, we need to execute the next instruction. That means that it is also a conditional branch instruction. Did I make myself clear? What is a conditional branch? We are branching to 25th instruction. If the condition gets satisfied, what is the condition? If it becomes 0 right after incrementing. Yes or no? Making sense or not? Hi Krishna. Yes or no? Yeah. So these are the memory reference instructions. Yeah. Now, once again, let me tell you, rather than emphasizing on the operation, kind of an operating that is performed, here emphasize on this. Opcode is equal to 000. Watch only the least significant 3 digits of the opcode. If the opcode is 000, AND will get performed. 001, add will get performed. 010, load will get performed. 011, store will get performed. 100, BUN will get performed. 101, BSA will get performed. What is BUN? Jump. What is BSA? Call. 110, ISZ will get performed. That means that my total memory reference instructions are in between 000 to 110, and opcode is of 3 digits. 3 bits are from 000 to 111, but out of which 111 combination we did not use for the memory reference instruction. So 111 combination is just reserved for register reference and the IO instruction, which I am going to explain you by tomorrow. I hope you got the point. And as of now, if you have any doubts, please shoot it right now. Otherwise, I'm gonna take you people to the register reference instructions in the very next day, that is tomorrow. So are we done for today? So far, what happened in this session? Let me give you a recap. Let me explain you total in a nutshell. We have just discussed about what exactly is a CPU. CPU is a collection of 3 entities: a register set, control unit, and the ALU. I explained about the control unit and ALU simply. Now the register set we need to focus more on, because during the execution of the opcodes, what is our class right now, we require to discuss about the registers, right? There are several registers. Altogether, we do have 8 special purpose registers, right from the program counter to the output register. Okay. Now, we are designing the opcodes. opcodes, we do have a provision of 3 digits. Using the 3 digits, we can accommodate a maximum of 8 opcodes. Okay, some opcodes are and add load store, example opcodes, and total opcodes will be divided into 3 categories: memory reference, register reference, and the IO instructions. In this session, altogether, we discussed about all the opcodes of the memory reference instructions. That means that for all these instructions, the operands are collected from the main memory. Tomorrow, we are going to discuss about those opcodes for which we are going to collect. We are going to collect the data, the operands from the processor's registers itself. Okay, so tomorrow we are going to cover register reference instructions. Day after tomorrow, we are going to cover about IO instructions. That's it for the session. Thank you so much. If you do have any doubts, please shoot it right now. Any doubts, or are we done? Okay then, that's it from the session. Aneel Prasad Sir is signing off, but before which, I request you people to please like and share the session and subscribe to this channel as much as possible if you haven't already yet. Thank you so much. That's it from the session.